curious minds. In a world full of secrets and shadows, every question leads to another mystery. Let's explore what lies beneath the surface. In this deep dive, we're venturing into the perplexing realm of mysteries at sea. We'll be navigating the often uncharted waters of human error in marine accidents, then submerging into the intriguing science behind methane hydrates and the sudden, powerful emergence of rogue waves. We'll even touch on the enduring enigma of the Bermuda Triangle. Our exploration draws from detailed accident reports, scientific investigations into deep-sea formations, and insightful discussions on extreme ocean waves. Our mission today: to understand the underlying factors that contribute to maritime incidents, separating solid critics from captivating speculation, and to truly appreciate the powerful and complex forces that govern our oceans.
It's a compelling arena, definitely. This intersection of human actions and the raw power of the ocean. When things go wrong at sea, the initial tendency, is often to focus on the crew. But as our look at National Transportation Safety Board reports from, 1975 to 2017 shows us, well, the reasons behind these incidents are often far more complex than simply pointing a finger at those on board.
Absolutely. And while numerous studies suggest human error is a major factor in maritime accidents, some estimates put it as high as 60 to 90%, our deep dive into the NTSB data reveals a really critical nuance. Yes, human error is significant, but it's not always solely or even primarily the fault of the ship's crew. In fact, when we isolate it, crew error alone accounted for just 32.2% of the incidents examined. So the headline here isn't just human error, it's that maritime safety is a much broader system involving numerous players, and focusing solely on the crew might be missing a huge piece of the puzzle.
Exactly. And what's truly fascinating is the substantial role played by what the NTSB terms other people's error. This category, which includes maritime pilots, company staff ashore, even the crews of other vessels, well, it accounted for a significant 26.9% of incidents on its own. And it contributed to another 15.9% of cases in combination with crew error. So if we connect this to the bigger picture, it strongly suggests that a considerable portion of maritime accidents involves a much wider network, individuals and organizational factors beyond just the ship itself.
Right. And when we dig deeper into this other people's error, the involvement of maritime pilots, particularly in incidents involving cargo and passenger ships, is really striking. They were implicated in a substantial 42.62% of those cases. That's huge. This raises a really important question about the effectiveness of coordination and communication protocols, between pilots and the ship's bridge team when vessels are navigating in pilotage waters.
Indeed. And the NTSB analysis further breaks down the types of errors made by the crew themselves. Navigation errors, things like misjudgments, maybe overconfidence, misuse of equipment, and insufficient training or inexperience emerged as the most frequent overall category. Following closely were deficiencies in pre-trip or maneuver planning, along with significant communication breakdowns, both within the crew and with external parties, like those pilots we just mentioned.
It's quite telling to see how these error types vary depending on the kind of vessel involved, isn't it? For example, fatigue appears to be a more significant contributing factor in accidents involving fishing vessels, which likely reflects the often demanding and, extended operational periods.
Makes sense.
Conversely, communication breakdowns with pilots seem to be more prevalent in cargo and passenger ship incidents.
Which leads us to some important implications, right? The relatively lower rate of crew error in the cargo and passenger fleets could suggest that international regulations like the STCW Convention, the one setting standards for seafarer training, it suggests they are having a positive effect. However, the data also strongly points to a clear need for enhanced coordination and communication on the bridge, particularly when a pilot is on board. That seems critical. Furthermore, the higher incidence of crew error on tugboats, potentially linked to the inherent challenges of navigating in confined and often congested waterways. That definitely warrants further attention in terms of training and operational procedures.
It really challenges that simplistic idea of crew error being the sole explanation. These investigations reveal a much more complex interplay of contributing factors, highlighting that the mysteries behind maritime accidents often lie in the intricate interactions between people, technology, and organizational systems, rather than just individual mistakes. So having navigated those complexities of human factors, let's now chart a course into a completely different kind of underwater enigma: methane hydrates.
A true shift to the deep indeed. Far beneath the ocean's surface, we encounter these fascinating, almost otherworldly icy structures. Methane hydrates are essentially clathrates. Think of them like tiny ice cages built by water molecules, specifically arranged in a geometric pattern called a dodecahedral shape. It's quite beautiful, actually, under a microscope. These cages trap methane molecules inside, although, importantly, there's no direct chemical bond between the water and the methane.
So where do these intriguing formations originate? It sounds like something straight out of deep sea exploration, very mysterious.
Well, their formation is tied to the activity of methanogenic archaea. These are microorganisms that thrive in the sediments of the deep ocean and also in permafrost regions. These archaea produce methane as they decompose organic matter, but under conditions of intense pressure and very low temperatures. Over vast periods, this methane can become encased within those water molecule cages, forming the stable methane hydrate structures we find in these deep-sea environments. What's truly fascinating is that these seemingly inert, icy structures hold a significant amount of energy and are actually quite sensitive to changes in their environment. It reminds us that even the deep ocean is far from static.
But stable in the deep doesn't necessarily mean they remain unchanged forever, right? What kind of disruptions can affect these icy formations?
Precisely. While methane hydrates exist in a solid state under specific deep-sea conditions, they are susceptible to temperature fluctuations. If the surrounding temperature increases, whether due to geological activity or maybe broader oceanographic shifts, the hydrates can become unstable. This instability leads to the release of the trapped methane gas, which often rises through the seafloor, sometimes visibly as methane seeps. You might see gas bubbles appearing on the surface or becoming trapped beneath seafloor features.
Wow. It's a powerful reminder that even in the seemingly tranquil depths of the ocean, there's a tremendous amount of dynamic activity taking place. These hidden icy structures, with their potential for dramatic transformation and the release of significant amounts of methane, well, they certainly add another layer to the unpredictable nature of the marine world. And here's where it gets really interesting, as we now turn our attention to another powerful and often unexpected ocean phenomenon: rogue waves.
Rogue waves. Yes, the very name conjures images of colossal walls of water seemingly appearing out of nowhere. Historically, these giant waves were often dismissed by many as mere mariners' folklore, sort of tall tales. But a growing body of evidence has dramatically shifted that understanding. That New Scientist article we looked at really highlights this. It's incredible to think that these weren't even considered real by many for so long, despite mariners' first-hand accounts. It really underscores how much we're still learning about the ocean's extremes.
And some of those mariner accounts are truly awe-inspiring, almost unbelievable. Think about Ernest Shackleton's harrowing encounter during his voyage in the James Caird. He vividly described a wave of such immense scale, utterly unlike anything he had witnessed in decades at sea, a mighty upheaval of the ocean, he called it. It's almost impossible to fully grasp the sheer terror and maybe wonder of confronting something like that.
Indeed. And Shackleton's experience is just one of many. The still-debated disappearance of the cargo ship mentioned, with compelling evidence suggesting an unlaunched lifeboat was twisted by an enormous force high above the normal waterline. And the real-life events that inspired the perfect storm, they all underscored the devastating power that these extreme waves can unleash.
So, what exactly is a rogue wave? How do scientists define it? Is it simply defined as an exceptionally large wave?
Operationally, yes. A rogue wave is often defined as a wave with a height more than 2 or 2.2 times the significant wave height. That significant wave height, it's a standard measure used by oceanographers, representing the average height of the largest one-third of waves. So it gives us a sense of the typical wave conditions.
Okay.
However, from a scientific perspective, there's also significant interest in waves that appear unexpectedly large within a group of much smaller waves. You know, the ones that defy simple statistical probabilities.
Yeah.
They just seem to pop up.
And the dangers posed by these rogue waves are substantial, aren't they? It's not just a threat to ships. Offshore platforms and even coastal structures are vulnerable too. I recall reading about the pressure measurements taken from the Admiralty breakwater. The sheer force of a breaking rogue wave is staggering.
Absolutely. The pressure exerted by these breaking waves can be immense, far exceeding the structural limits that many ocean-going vessels are designed to withstand. The physics behind the formation of large waves involves several contributing factors. There's the transfer of energy from the wind to the water's surface, obviously, nonlinear interactions between different waves, and crucially, the refraction or bending of waves as they pass through strong ocean currents. The Agulhas Current off the coast of South Africa is a well-known example where this happens.
It sounds incredibly challenging to predict when and where these rogue waves might actually occur.
It is indeed. Observing and statistically analyzing rogue waves is hampered by the inherent limitations in collecting sufficient data in such unpredictable and extreme conditions. It's hard to be in the right place at the right time safely. However, scientists are actively investigating various mechanisms that could lead to their formation. One key concept is the Benjamin Fair instability.
Benjamin Fair.
Yeah. Essentially, it's a phenomenon where waves in a relatively uniform series can start stealing energy from their neighboring waves, causing some to grow dramatically taller while others shrink. It's a kind of focusing effect. Wave breaking itself also plays a complex role, both as a potential consequence of extreme wave height and perhaps as a factor that can limit just how large a rogue wave can ultimately become. It's complicated.
What about those accounts of three sisters, groups of exceptionally large waves appearing in quick succession? Do they fit into our understanding of rogue waves?
That's a good question. Interestingly, while crossing seas, where waves come from different directions, might not be as prone to the specific kind of instability that generates solitary rogue waves. The rapid superposition or overlapping of waves from these different systems could still result in very large waves, where the usual height-limiting effect of breaking might be reduced. So maybe not the same mechanism, but still dangerous. The research in this area is definitely ongoing, and more comprehensive real-world observations are crucial to fully understand these complex and often unpredictable events.
They truly do emerge like mysteries from the deep, don't they? Defying our typical expectations of the sea and adding another significant layer of peril to any ocean voyage. This all naturally makes you think about those enduring maritime legends, such as the Bermuda Triangle.
Ah, the Bermuda Triangle. It has certainly captured the imagination of people around the world as a geographical area associated with the unexplained disappearances of ships and aircraft. Lots of stories there. Now, while the sources we examine today don't specifically focus on offering explanations for those particular events, it's worth considering that some of the factors we've discussed, human error occurring in unexpected ways within complex systems, the potential for extreme and sudden natural phenomena like rogue waves, and just the sheer complexity and dynamic nature of the ocean environment itself. Well, these could conceivably contribute to maritime incidents in any location, including that infamous area.
Right. It suggests that while definitive answers for the mysteries specifically in the Bermuda Triangle might remain elusive or debated, having a deeper understanding of the broader risks inherent in seafaring and the powerful forces at play in the ocean provides a valuable context. Perhaps hinting that what seems unexplained might sometimes have roots in the complexities that we can begin to understand.
Precisely. It brings us full circle, really, to the fundamental complexity of the ocean. From the inherent fallibility of human decision-making in demanding environments to the hidden power of things like methane hydrates lying beneath the seabed and the sudden, unpredictable fury of rogue waves. So many interconnected factors can contribute to the enduring mysteries of the sea.
Some answers only raise more questions. Until then, stay curious.